Hi, my name is Frederick Kane. This is my Physics 2 Lab 1, the charged tape experiment. Now, the purpose of this lab experiment was to understand and see how electric fields in the real world interact with one another, specifically in the concept of a charged tape, and ultimately attempt to compute the charge of a singular piece of tape in this experiment and determine the signs of an object. We did this using physical equations and some of the main principles listed below. It's important to note, force equals mass times acceleration, aka Newton's second law, should also be up here. Coulomb's law is going to be stated right here. Force equals the constant times charge 1, charge 2, divided by the distance between the two. Another thing that's important to note, basic concept, like charges repel. Each tape was treated as a point charge in this experiment, with charge concentrated to a center of mass. Using these formulas and the knowledge that I'll explain later, our results resulted in the two pieces of tape repelled one another and were shown to be positive charges, or two pieces of charged tape. The charge of each tape was 1.3 times 10 to the negative 8 coulombs, and the two pieces of tape were deficient by 8 times 10 to the 10th electrons. Now, the system was an entire piece of tape treated as a point charge, and the surroundings were all other objects/forces, primarily gravity for these experiments, specifically the second part. Our initial conditions: tape mass was 2 times 10 to the negative 4 kilograms, length was 0.2 meters, width was 0.002 meters. Part 1 of our experiment was to charge the tape. We laid one piece of tape on top of another and stripped it off fast, which gave it a charge. Then we observed whether these two tapes were repelled or attracted one another, and they were shown to repel one another, suggesting that they have the same charge. What we found was, when given a pen of a known to have a negative charge, and we brought that close to our charged tape, we found that the two attracted, suggesting that the tape itself was positive, because it was attracted to a negative object. Now, the second part of our experiment was to see the displacement between two charged tapes when you put one on another, like one on another, as witnessed here. B tape was kept stationary, and in doing so, we did so in a manner that would allow the system to come to static equilibrium, meaning that the piece of B tape was not moving, neither was the A tape. The distance of displacement between the original position of tape B and the second position after the interaction between the other charged tape was 0.003 meters. Now, since our tape was in static equilibrium, then that force must have been equal to 0. And if we were looking at just the y direction and really only considering the electric and gravitational forces, that would mean that the force of our gravity has to be equal to the force of electricity, because they are acting in opposite directions for it to not be moving. Now, like I said, force equals mass times acceleration, and that's the equation we'll be using to figure out the force of our gravity, where our mass was 0.0021 kilograms, to be more precise from earlier, and our g value was 9.8 meters per second squared, which resulted in a force of 0.00206 newtons. Now, that's the value of our Fg, but what about the Fe? Now, our goal is to determine the charge of one of our pieces of tape, so we want to solve for this Q value right here. Now, we're assuming that the two pieces of tape have the same charge, which is why this is Q squared and not Q1 times Q2. Now, after some rearrangement and solving for Q, we set our D value equal to 0.003, which is what we calculated. We found that our Q value is 1.34 times 10 to the negative 8 coulombs. Now, we also wanted to model this in a coding sense, so I use GlowScript Python here. You can see that I set all my constants right here. This is our constant in our Coulomb's law equation, gravitational constant, mass of our tape, displacement, and the charge that we calculated earlier. Now, we can see that our force of gravity is gravity times mass times the direction, which is in the negative direction, and then the opposite for the positive direction with the electric charge, which is also using Coulomb's law. Source of error: treated the tape as a point charge instead of a real-world scenario where it's not as such the charge is distributed throughout the piece of tape. We also ignored air resistance and assumed it to be negligible, which could have possibly impacted our calculations. We also assumed that both tapes have the exact same charges and lengths, which is safe to assume because the difference would not be too drastic. However, it is still something that is a very possible minimal source of error. And the fourth part is hand coming in contact with U tapes, we'll explain here in a second for our what if and why. Now, what if electrons and protons switch charges? Fundamental concepts would not change. Like still repels like, opposites still attract. This would not really change our experiment at all. Now, if you were to look at this on a piece of paper and draw out the directions of electric fields, you might see them changing directions because electrons would change charges and therefore not attract but repel in an electric field. But in a fundamental concept, a real concept, that would not change too much of what's going on. And why is it important to handle the U tapes as little as possible? When one charged object comes in contact with another, or specifically a neutral object, in this case, are assumed to be neutral, the charges will distribute and go on to this other object, which can take away the charge from the U-tape, maybe making our experiments less reliable. Because if one piece of U-tape touches another one too much, then they don't have the same charge, and that can mess up our equation used here, where we assume that Q was the same value for both of them. Anyways, that's it for my lab. I hope you have a wonderful day. Thank you so much.